In this video we're going to finish up section 5.4, Exponential and Logarithmic Equations, and this is the second day we're spending on it. We're going to get into the more complicated exponential equations today, or no, it's the logarithmic, excuse me. So solving logarithmic equations. To solve a log equation you can write it in exponential form. So here in the top we have the ln of x equals 3, that is logarithmic form. And to get rid of that ln, that natural log, we're going to exponentiate each side of the equation. So we're going to raise each side of the equation to a base of e, and these are going to become our exponents now. So here we have e raised to the power ln of x is equal to e to the third power, again exponentiated each side. And now this e raised to the ln power cancels. So we got x out of that natural log function. Now it's just x equals e to the third power. And remember, e is just a number. We could punch that into the calculator and get the approximate decimal equivalent. Again, this procedure is called exponentiating each side of an equation. You could think about the natural log as sort of a prison, and the x is trapped in the prison. How do you bust that x out when you're solving for the variable? We're going to raise each side to a power to a base of e. And then that e to the natural log cancels, and our x pops out. So in example 6, solve the logarithmic equations. The first one is the ln of x equals 2. Well, just like that last example, we are going to exponentiate both sides of the equation. So now we have e to the natural log of x power, and that e to the natural log will cancel, and we'll have x equals e squared. And e is just a number. We could punch that in our calculator and get a decimal, which would be approximately 7.389. In letter B, we have the log base 3 of the quantity 5x minus 1 is equal to log base 3 of the quantity x plus 7. Well, here we're not going to have to exponentiate each side. We have log base 3 is equal to log base 3. So by the one-to-one property, we know that 5x minus 1 is equal to x plus 7. And let's subtract x from each side. So this will come down to a 4x now, 4x. And equal to, let's add 1 to both sides to get rid of this minus 1. 7 plus 1 is 8. So now we have 4x equals 8, and divide by 4, of course, x is equal to 2. Let's see here in letter C, we have log base 6 of this quantity, 3x plus 14, minus log base 6 of 5, and that's equal to log base 6 of 2. Well, in the part B above, we used the one-to-one property. We had a log base 3 was equal to a log base 3. So on the left side of the equal sign, we had a single log base 3. On the other side was a single log base 3. Here we have log base 6, and now on the left side we do have a quantity being subtracted, one log minus another. So before we can apply that one-to-one property, we're going to have to condense that left-hand side. So let's see here. We have log base 6 minus log base 6. So that tells us this is going to be a log of a quotient. Here's our numerator, 3x plus 14. And that's divided by the denominator, 5. And that's equal to log base 6 of 2x. Okay, now we can apply the one-to-one property. A log base 6 is equal to a log base 6. So we can ignore the log base 6's, and we can just have 3x plus 14 to all divided by 5 is equal to 2x. And now we just have to solve for x. So multiply each side by 5, and we'll have our 3x plus 14 is equal to 5 times 2x is 10x. Let's subtract 3x from each side. So now we have a 7x over here, and that's equal to 14. Divide by 7. X is equal to 2. And we got a little caution. Remember to check your solutions in the original equation when you're solving equations to verify that the answer is correct and to make sure that the answer lies in the domain of the original equation. And you can take my word, you know, the last couple examples those do. If we took our answer and checked it back into the original equation, it is going to work. And remember, one key point here is you can never take the log of a negative number. So here I'm log base 6ing in my original equation. If I plug this positive 2 in for x, I'm going to get 6 plus 14 is 20. So that is going to be a positive number, and I can take the log of it. If I plug the same 2 in here, log base 6 of 2 times 2 would be log base 6 of 4. And again, I do have an answer for that. But we do have to watch for those extraneous solutions. Example 7. Solve 5 plus 2 times the ln of x is equal to 4 and approximate the result to 3 decimal places. Okay, so we're taking the log of our variable. Kind of again, like I said at the beginning of the video, the ln of x. X is in jail, and we have to get that x out of jail by using an exponential. The first thing we're going to do here, though, is solve for, or get the ln isolated. So I'm going to address this 5 out front. We're going to subtract 5 from each side. And then we're going to have 2 ln of x equals -1. And divide both sides by 2. So now we have the ln of x is equal to -1/2. Okay, on the left we have isolated the natural log function, so now it's time to exponentiate each side. So we're going to base e to each side here, and now the ln cancels, and we're left with x equals e to the -1/2 power. And that, the directions did say approximate the result to 3 decimal places, so this is something to the -1/2. We could put that into our calculator. And if we don't have a e to the -1/2 button or the negative exponent there, we could always rewrite that as 1 over the square root of e. And if you punch that in, you'll get approximately 0.607. Okay, example 8. 2 log base 5 of 3x is equal to 4. And we're going to again approximate this to 3 decimal, or no, it doesn't say approximate to 3 decimal places. That was the last example. So we'll just solve this, maybe leave it in a different form. First step, I want to isolate my logarithm, so I'm going to divide both sides by 2. And I'm going to have then log base 5 of 3x is equal to 4 divided by 2 is 2. So now I'm going to exponentiate each side. You know, in the last one we did exponentiate with base e because we had the natural log we were dealing with. Here it's log base 5. So I'm going to give each side now a base of 5. So I have 5 raised to this power, log base 5 of 3x, is equal to 5 to the second power. So the 5 of log base 5 will cancel, and we're left with 3x equals 5 squared, and 5 squared is 25. And then divide both sides by 3. X equals 25/3. And that's one way to get the right answer. Now there is an alternate method depending on how we initially approach the problem. We could have used one of our properties of logarithms to say, well, we got this 2 here in front of the log. I'm going to make that hop up top and become an exponent. And then that would have been log base 5 of the quantity 3x squared equals 4. And then here I could raise each side, or exponentiate each side. So the 5 of log base 5 will cancel, and I'm left with 3x quantity squared is equal to 625. And right here I could square root each side. Now the square root and the square cancel, so we're left with just the 3x is equal to the square root of 625 is 25. Oops, that's an ugly 5. And that puts us right back to this point in our first solution to this. 3x equals 25, divide by 3. X is 25/3. Example 9. And here they do warn us, check for that extraneous solution. And we'll see what it looks like when we do find one of those extraneous solutions. So on the left, log, this is common log of 5x plus the log of quantity x minus 1 is equal to 2. Before I exponentiate each side, I want to condense the 2 logs on the left. So log base 10 and plus a log base 10 is going to be the log of the product. And the product is going to be of 5x and x minus 1 equal to 2. And I guess we could distribute the 5x throughout that set of parentheses right here. So that'll give us the log of 5x squared minus 5x, and that's equal to 2. Alright, since our log is a common log or base 10, it's implied that it's in there, I'm going to exponentiate each side to a base of 10. So here the 10 raised to the log base 10 powers will cancel, and we're left with just the exponent there, the 5x squared minus 5x. And that's equal to 10 squared is 100. Alright, now it looks like we got a squared term and a single power term and a number. We're going to get this all equal to 0, and factor is probably the root we're looking for. So I'm going to subtract that 100 from each side. 5x squared minus 5x minus 100 equals 0. And then let's divide everything by 5. Every term gets divided by 5, even the 0. So we're left with x squared minus x minus 100 divided by 5 is 20 equals 0. So we need the factors of negative 20 that add up to negative 1. And it's going to be 5 and 4, x minus 5 and x plus 4. Minus 5 plus 4 is negative 1. If we multiply them, we get the negative 20 that we were looking for. And then we set each factor to 0. So we get x equals positive 5 and x equals negative 4. So we have two solutions, and let's check those in the original equation. So the original equation is right here, and that is the log of 5 times x plus the log of x minus 1 is equal to 2. So if I plug in the 5, I would get the log of 25 plus the log of 5 minus 1 is 4. And is that equal to 2? Let's see if all those buttons are on our calculator. So log of 25 plus log of 4. 25 log plus 4 log equals exactly 2. So it did work. Let's see what happens when we plug in the other answer we got, negative 4. So we'll have the log of 5 times negative 4 is negative 20. Uh-oh, that should send up a red flag. Plus the log of negative 4 minus 1 is negative 5. Ooh, another red flag. Does that equal 2? Well, let's see. 20 negative, and we want to log it. Invalid input. Cannot take the log of a negative number, and we're doing that twice in here. So we do, through the exponentiation process, have extraneous solution. We can't take the log of a negative number, so that negative 4 is our extraneous solution. And let's see what our little study tip says here. Notice in this example that the logarithmic part of the equation is condensed into a single log before exponentiating each side of the equation. Alright, 3 practice problems. If there's a number 101 in your notes, cross it out. Give these huddle problems here a try. Pause the video, try them, start it back up, see if you got them right. Tonight's assignment is just a worksheet. Okay, let's give these practice problems a try. And the directions say to take them to 3 decimal places. Let's see here, just a nice slow pitch right across the plate. The ln of x equals negative 3. We want to get that x out of there, so we have to exponentiate each side to a base e to get rid of that natural log. So on the left, we're left with x equals, and then e to the negative 3rd power. Is that something I can do on the computer calculator? E to the negative 3rd. I don't see the E key. It might be hidden in there somewhere else. Oh yeah, okay, there's our e to the x. If we hit e to the x, I'm going to give the power in there of negative 3 negative, and then inverse e to the x. And we get 0.049787. They want it to 3 decimal places. So it looks like 0.05 is going to be good. 0.050. 0.050 approximately. All right. Number 85. Not too difficult here. Again, it's already set up. We have the ln of 2x equals 2.4. So we are going to exponentiate each side. The e to the ln cancels, and we're left with 2x is equal to e to the 2.4 power. So divide by 2. X equals e to the 2.4 power divided by 2. So let's clear this out. 2.4, and we're going to inverse. That's our e to the x, so there's our e to the 2.4 power. And then we're going to divide that answer by 2. And we get 5.115, so we're going to round that up to 5.512. 5.512. All right, number 87. Oh, supposed to be an eraser. There we go. The log of x equals 6. Remember, if it's just log log and you don't see a base, there's an implied base 10 there. So we are going to exponentiate each side to a base of 10. So the 10 log base 10 is going to cancel, and we're just left with the x equals 10 to the 6th power is a 1 with 6 zeros after it, or a nice cool million. There we go. Again, the assignment for tonight is just a worksheet. Make sure you get that from me.